Remember how we had the Aldol condensation back when we looked at ketones and aldehydes and nucleophilic addition? We're going to get it again, but this time it's going to be with esters. So I just wanted to real quickly tie back to what we remembered or what we potentially remembered about those. So when we were looking at the aldol reaction, what we were concerned about is these alpha hydrogens. Those alpha hydrogens are acidic, and depending on the base used, are varying abilities to remove those. Okay, but sodium hydroxide is more than strong enough. It can come in deprotonate, which gives us that big active nucleophile. That active carbon nucleophile might be a bit of a questionable thing to form because carbon isn't good at stabilizing electrons, but we have that internal resonance. This is that keto-enol tautomerization, and it's really kind of the center point of our keto-enol tautomerization that's explaining this. But once we've got that nucleophile, the reaction can do a nucleophilic addition, and we would continue on through the rest of that, yada, 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 potentially even doing a condensation, or likely doing a condensation, because there's still alpha hydrogens that are acidic that could be removed. So the big things that we got out of this was that acidic alpha hydrogen, and that we ended up with a nucleophilic carbon, okay, via the enolate. So those are important aspects to remember because those same things are going to carry across when we move to our acid derivatives. And then, sure enough, we've actually already seen this. If you think back to the Hell-Volhard-Zelinsky reaction, which I think was actually the last lecture, in that case, what happened was that we took these alpha hydrogens and were able to run a substitution reaction with them. And we were able to do that because we first converted it to the acid chloride, and now under acidic conditions or mildly acidic conditions, those hydrogens are slightly acidic, and can be removed to give us again that active nucleophile, which could then react with our Br2. Okay, so it's that alpha hydrogen again that's coming in that we've seen in the Hell-Volhard, and we're going to see it here when we look at the Aldol-like reaction. Why the air quotes? Because of course somebody had to attach their name to it. This is probably my biggest soapbox naming event because it's the same chemistry that we've seen everywhere else. And I'm getting a phone call from daycare, so I'm going to have to answer that. So not a big deal. So we'll come back. Aldols. So let's go ahead and move on. What are we talking about? As soon as we do an aldol now with an ester, it gets called a Claisen condensation. Okay, and some of the reason on why we might do a name shift for this. Okay, if we were to say first look at these structures, sorry, weird screens happening. If we were to go through and look at this, and we referenced these hydrogens, and we say compared those to the hydrogens of an aldehyde, well, hopefully what we would note is that those red hydrogens in comparison of the ester, as opposed to the now blue hydrogen of the aldehyde, are less acidic. Okay, that is a confusing one, so let's walk through that real quickly. Why are the ester hydrogens less acidic? Well, it is all going to tie back to that oxygen. The oxygen of the ester does resonance to donate inwards. Those electrons now go in towards that positive charge. The thing that's making those hydrogens acidic is that positive charge, right? Because we can do a resonance stabilization. So in the case of the ester, there's a competing resonance structure, which nullifies the acidic ability. If we go through and looked at the aldehyde, there is no competing resonance. Okay, what does that mean? That means the conjugate base for the aldehyde is more stable than it is for the ester, which therefore means the ester is less acidic. Okay? So on first blush, we might go through and say that the ester should not react anywhere near the level that an aldehyde or a ketone would. Okay? But it does. Because it did, now someone gets to attach their name to it. Is the chemistry really new or different or exciting? We'll look at it here and you can decide, but I would argue no. Okay, it's still the same process. Okay, so what happens? Well, we have this nice strong base. Okay, note we have that metal non-metal bond, so we can get rid of the spectator ion. We've got our acidic hydrogen. Our electrons can come down, and we can go through and form, whoops, so I drew too many bonds, we can form our enolate. That does have resonance. I'm not going to evaluate the resonance with the ester oxygen, but I am going to go through and look at the resonance, giving us the active nucleophile. Now what goes through and happens is that we can react this with another ester, nucleophilic addition, and I have gotten way excessively carried away with the size of this, which is a bit unfortunate. Here's our new bond. There's the O minus. There's our CH3, and then there's the O ethyl. Electrons come back down. We kick out the best leaving group being that guy. Yeah, sorry, I do apologize for crowding it here. And we would have what we might go through and say is our final product. Okay? But the observant eye might note that what we're kicking off is a negative oxygen, and what we started with was a negative oxygen. So at this point, this reaction is going to be heavily equilibrium dependent, and if anything, we aren't going to get a lot of product. Well, if we don't get a lot of product, that means it's not a useful synthesis, and thereby no one would get to attach their name to it. And so this is potentially one of those clutch points on why someone would get to stamp their name on top of this. We're following the same route that we did with the aldol. Okay? We don't get that same kind of condensation, at least right away. Okay? One of the things that's kind of interesting here is that we still have acidic hydrogens. And those purple hydrogens, if we compare back through to the first hydrogens we removed, that would be those red ones, those purple hydrogens are even more acidic than the red ones. Okay? Why would they be more acidic? Well, if we go through and evaluate it, we get lots of resonance. I can't believe I drew this so horribly spaced. That bothers me a lot. Hopefully it doesn't bother you as much. And if we look at our result, there's kind of our enolate, our CH3, and we would form that structure. But as we've already noted, the enolate is not particularly stable, and it likes to revert back to the ketone. Okay? But to do that, I would need a hydrogen. Note step 2. Step 2 is when we bring in H+. Why did we need H+? Well, if we look through our mechanism, that product that we're forming, the purple star, looks like a neutral stable product. Under basic conditions, we can do that deprotonation. To finalize the reaction, our electrons come back down, pick up the H+, and we would end with our final structure. And for those of you that are very observant, the purple star structure and that blue structure are identical. Okay? So Why? Right? Why go through those extra steps? Well, those extra steps we go through because the chemistry dictates that we need to do it. How do we know the chemistry dictates we need to do it? Well, as we addressed when we got to that purple star, equilibrium being equal, if we assumed flat, perfect equilibrium, this gets at best a 50% yield. Well, that's pretty crappy. Okay? If we go through and take a look at that very next step, okay, that base, okay, in particular this acid-base step, that acid-base step is irreversible. You are forming an incredibly stabilized structure. That stabilized intermediate is what's driving the Claisen condensation, okay, and why we get the product that we get. Okay? Without that acid-base step, that second clutch acid-base step, we don't get a Claisen condensation. We get nothing. Okay? So the sheer fact that this reaction works could be a reason to associate a name with it. Right? And so that's what you need to remember. So again, we've got the alpha hydrogens that are acidic, not as acidic, but acidic. Okay? The base goes through deprotonates. We do our nucleophilic addition. We do our nucleophilic elimination. And then we do a clutch second acid-base step. We have to have that second acid-base step. If it isn't there, we don't do the reaction, or we don't run the Claisen. And that's a very important statement to make. You have to have 2 alpha hydrogens. If you only got 1, nothing happens. You need 2. Okay? So, mechanism, very prettily drawn. Thank you to our textbook for having produced that. And note they're showing some of the resonance. I would argue that they probably should have shown kind of the most important resonance, which is the reason why this whole reaction works, the resonance of this structure. If we go through and look at the reactions, equilibrium, 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 not equilibrium, not equilibrium. Okay, it is those non-equilibrium steps that are actually driving the reaction forwards. Okay? So with that, are there kind of complications that we should be aware of? Okay, so first and foremost, what we can do is take a look at a special ester to the upper left. That would be known as a malonic ester. Malonic, yeah, let's just say that. We'll talk about that one, I think, in the next video. If we've got ethoxide, what could potentially occur? Okay, well, we just addressed, right? We need those alpha hydrogens. Well, do we have 2 alpha hydrogens? Well, yeah, we do. We have them here. So wouldn't we just go through and run our standard reaction where we then hook this up to one of our carbonyls, which could then continue out, right? Negative, this is our, and we could do all of our fun stuff, kick that, kick that. And if we wanted to just kind of shortcut it, couldn't we have just gotten that? Right? Okay, all we've done is now linked those. Okay, you could do a similar stacking effect that we've done in the past. Okay, and for whatever reason, I picked the diester, which makes this a lot messier, but we can at least see all those pieces. So yeah, we could run the Claisen, right? But is there another positive floating somewhere in there? Because in this case, our ethoxide acted as a base because it deprotonated the hydrogens. Well, couldn't ethoxide also act as a nucleophile? Is there an electrophilic site somewhere in this molecule? Well, yeah. Okay. In which case, we would end up doing a transesterification. So on top of the base product we would get, we would also be getting the transesterification product, where it's an ethyl now. Well, there was another one. We could have also gotten the system where it had double esterified. Right? And we have the condensation process, the actual Claisen reaction. So if we aren't careful with the selection of our base and or nucleophile, we could get a whole myriad of different products, which ultimately then means which one's which, and it could be a complicated mess. So how could we simplify this to ensure that the only result I have to worry about is the base result and not the nucleophile, because I don't want that nucleophile coming in and doing nucleophile chemistry. Okay, well, it's relatively simple. The base and the leaving group need to be the same. If I switch up that base and instead of using O-ethoxide, I use O-methoxide, if it acts as a nucleophile and attacks our electrophilic carbon, and we kick out a leaving group of O-methyl, what would be left behind? Well, O-methyl. So the nucleophilic attack is still happening, but it doesn't change the structure. Right? So one of our complications behind this is that the base choice that we get to use is very constricted based off of the leaving group functionality of our ester. Okay? So this kind of simplifies things because now we don't have to worry about kinetic or thermodynamic or any of that because I only get one base. I have to use that base. I'm not allowed to use sodium hydride, LDA, okay, because those species could potentially mess with our end result. The other clutch step that we have to worry about is being addressed in the bottom case. Okay, so let's walk through the cheat, if you will. We would draw out our structure with our alpha hydrogen, right? So there's the first case. That would be our nucleophile. That would attack our electrophilic position. We'd have our O leaving, right? So there's our new bond. When that came down, it would eject that. So as a cheat, all I'm doing is connecting those two positions and getting that answer. Okay? You say, well, doesn't that work? Isn't that what I get? And it turns out for this reaction that we actually get no reaction. If we look at it, all the bonds seem to align. Why wouldn't this reaction work? Well, what we've shown up to this point, okay, as far as our cheat, gets us to what the Claisen product would be, assuming each of the mechanistic steps were valid. Right? Remember, there's a clutch mechanistic step. We have to have 2 alpha hydrogens. And if we look at that position, there's only 1. We need that second alpha hydrogen so that we can actually continue the reaction to form our resonance stabilized intermediate. And that becomes an important structure because that one step is not equilibrium. Every other one beforehand is equilibrium. Okay? So in this case, since I don't have 2, I don't know why I'm showing sigmas. It suddenly dawned on me. 2 alpha hydrogens. Because I don't have those 2 alpha hydrogens, that critical step in our mechanism can't happen. Because it can't happen, we end up seeing the reverse reaction kind of dominate, and we end up getting no result. So, big summary to our complications. We need, I didn't actually push that one all the way through. We need the base that is used to match the, ester leaving group. Has to be the same. And we need to ensure that our starting ester has 2 alpha hydrogens. If those conditions are met, then we can push through the Claisen. Okay? If we remember back with our aldol, we could do crossed aldol reactions. So in this case, we have 2 aldehydes. Was that 1, 2, 3, 4 butyraldehyde and ethanaldehyde or acetaldehyde. And if we really dig back, how many possible products could come out of this? Yeah, it was 4. It was a lot of products. So we don't want that many products. So the solution that we could have potentially worked out was that we switched it up and used a different base. That different base would be strong enough that it would form exclusively one nucleophile. Then I would add in the other aldehyde species to act as the electrophile and drastically cut down on the amount of products so that I only get one. Okay? So when we're running crossed aldols, we had to be careful to ensure that we get one nucleophile, one electrophile. Well, can Claisens run in a cross system? What if I look at the 2 esters down below? Okay. Note, in this case, we fixed one of the big issues that we talked about. Those are all looking at methoxide, which is good. Okay. And the other big thing that we could note is that they both have 2 alpha hydrogens. Okay. So we've got all of those big checks set up, allowing us to move forward with the Claisen. If we ran this Claisen, though, what could we expect? Well, there isn't really any difference in acidity between, say, that purple hydrogen and that red hydrogen, which means the base could come through and it could make the purple hydrogen structure a nucleophile, or it could have made the red hydrogen structure a nucleophile. If the red hydrogen structure was the nucleophile, then the purple hydrogen structure would need to be an electrophile. But if the purple structure was a nucleophile, then the red structure would need to be an electrophile. And they both are electrophilic because they both have that carbonyl carbon, right? Which means each of these structures can act as both a nucleophile and an electrophile, and we run into the exact same issue that we had with the aldol. We end up with 4 possible products. Okay, so that's not ideal. The way to go through and fix that is to try and limit some of that exposure in one form or another. Okay, because our base selection is pretty much limited to just the leaving group, okay, we really have to focus on the other part. We have to ensure that there's no alpha hydrogens. Okay, so that's our biggest fix. Ensure that one of your ester species doesn't have an alpha hydrogen. This prevents it from acting as a nucleophile or ever becoming a nucleophile, which limits the amount of products that we can get out. We could potentially also play with the bases. It becomes a little bit dodgier to deal with the bases, and so generally that's not the best strategy. Really what you're looking at is limiting that alpha hydrogen. Okay? Which gets us to the next point. We're just talking about alpha hydrogens. Do alpha hydrogens have to come from aldehydes? Do they have to come from ketones? Do they have to come from esters? Well, if we're talking about an aldol reaction, they have to be aldehydes. But as we noted back in that last unit, ketones could do it too, and we just grouped them into the aldol category. Well, Claisens have esters have alpha hydrogens as well, which means we can run Claisens, okay, doing the same mechanistic process. Well, if ketones can have alpha hydrogens and aldehydes can have alpha hydrogens and esters can have alpha hydrogens, what's to stop me from, say, taking an ester and reacting it with a ketone, or an ester and reacting it with an aldehyde? Well, ultimately, nothing. Nothing prevents you from doing that, which means we're getting what I'm calling a crossed AlDol-Claisen, where you're getting a aldol and a Claisen reaction happening kind of simultaneously. So they're also fair game because they allow for all of that same chemistry. alpha hydrogens to create nucleophiles, and the carbonyl is still electrophilic. Okay? In this case, the base does kind of become important, because if we use just a strong base, that strong base is going to react with this structure, giving us some active nucleophile and then some unreacted starting material, which means I get a nucleophile, an electrophile, and an electrophile, multiple products. So when we talk about running these crossed aldol-Claisens, we need to use stupid strong bases like our sodium amide, because now when the sodium amide reacts, it reacts entirely. It's not an equilibrium reaction, which means we don't get any electrophile. That means when we run the reaction, we can get the active nucleophile of our ketone reacting with the active electrophile form of our ester. It does show this happening as, actually it's not showing it as two steps, it's showing that first part all as one. Okay. Do we need to mix the base with our ketone, then add in the ester? Does the order matter? Yes and no. The ketone and the base should be mixed first, okay, so that the base is reacting with the ketone. But if the ester's in there, do I need to worry about the base deprotonating it? A little bit, but not too much. Okay, why not too much? Why would the base target the ketone, not the ester? That's right, good job. The ketone is actually more acidic than the ester because the ester has that competing resonance which stabilizes it and prevents it from acting as an acid. The base selectively goes to the ketone. Okay? That's what's going to drive that chemistry pushing forward, so you get crossed aldol-Claisens. Again, that's not a standard term, that's just what I call it, because if people can make up names, why the hell not? Okay, the last one, and this one is super irritating. With aldols, we could do intramolecular reactions. So couldn't we do an intramolecular Claisen reaction? Yeah, we can. Okay, just like we did with the aldol. For whatever reason, and I'm really baffled by this one, this is known as the Dieckmann condensation. The name is associated with it. Okay, this whole unit, as far as named reactions, drives me up the wall because all of the chemistry is identical to stuff we've already identified. They just use a different functional group. Oh my God, it's a different functional group. Name. Get your bloody name out of there and focus on the chemistry. Okay. Ultimately, again, you need a long enough structure so that you can form a 5 or 6 membered ring. That's one of the requirements. If we look at our ester structure, okay, we have the electrophilic sites for our esters, okay, depending on where the base reacts. And then we have our alpha hydrogens. And note the alpha hydrogens are going to be on the inside because the outside of these structures is those leaving group esters. Okay. For those of you being like, did it have to be a leaving group? Couldn't it have been a ketone? Yep, it could. Attach your name to that. Publish that and be like, oh, that's now the fart knocker condensation. That would be awesome if you could get a reaction named fart knocker. I would really greatly appreciate that. Become a synthetic chemist just so you can put that name and shove it down people's throats. We should probably focus. So the reaction occurs, we get that cyclization. Okay, note in this case, the nucleophilic carbon came from the red side, okay, and it came in and attacked over here. How do we know that? By looking at the product, right? Well, if we go through and look, the red part is still there, okay? And here you might see this and be like, well, that's obvious, I get it. You might not, which is okay. This advice is still going to help. Probably the biggest thing you can do, particularly for anything that you suspect is cyclizing, is to number your carbons. So I know I'm connecting carbon 1 to carbon 6, so I could draw out a 6-membered ring. And then I could go through a number 1, 2, 3, 4, 5, 6. Note that I counted kind of left to right, and note that I'm counting left to right because I'm trying to maintain that geometry so that I can get my ordering of those groups appropriate. At carbon number 1, I have my ester. I know there's not a lot of space there, but there's the ester. At carbon number 6, I have my carbonyl. Ta-da! There's the answer. Okay? And I've accounted for all the carbons appropriately. One of the most common mistakes that happens with these reactions is students deleting a carbon, okay, or adding a carbon in between. And so they would end up showing the carbonyl over here. So if you go through and number your carbons, you can vastly limit those issues popping up. Okay? So that would be my recommendation with these. Make sure you number your carbons so that you can ensure that you're getting the proper connectivity and you're showing where those groups are located. It is such a common mistake that I would fully expect those answer choices to show up in the multiple choice. Okay? Those are all difficult to nuance away from each other, particularly if you aren't numbering your carbons. So please go through and do that. And with that, I am late to my office hours, so we're going to go ahead and stop. Thanks for making it for the full half hour.